Ron Stouffer joined GFDL scientific staff over 30 years ago. Kind of amazing. After receiving a bachelor's and master's in state, he's now a senior research meteorologist in the climate dynamics for GFDL, where his research focuses on understanding and predicting the behavior of climate change. His work on the MOC, initially in collaboration with Summaries, certainly falls among the classics of the climate literature. Now, a second ago I emphasized both understanding and prediction, which is important in this case because, like most of his colleagues at GFDL, I've always found that when it comes to the predictive power of models, Ron is a realist more than an enthusiast. And frankly, for someone like myself and others who draw on GFDL, their understanding, the fact that we're dealing with a bunch of realists is extremely valuable to us. We who are not climate models. Ron has been a lead author, now called lead author of the IPCC, going back to the second assessment. He was also involved in the first assessment. And I can vouch by personal observation for his, not only his dedication to the process, but his centrality to it. If you count, as I've often to do, you'll notice that his articles are referred to over 50 times in the fourth assessment. Now, IPCC is charged with, again, assessing, and I personally interpret that to mean reviewing the scientific literature and making judgments about it. And it's that second point that I think many outsiders don't understand. And it's by far the most difficult and also the most important part of the IPCC process, the judgment part of it. It's in the exercise of judgments that many scientists, even very good ones, and I've seen this myself, kind of lose their heads and get carried away in their enthusiasm for particular findings, usually their own particular findings. And on the other hand, you get an equal number of scientists who are frozen by fear of departing from the literal meaning of findings to interpret them. And the assessments would fail if they were dominated by either attitude. Either people who went too far or people who were afraid to connect the dots. And it's in this realm that I think that Ron is really among the best. He never loses his head, and he's always willing to venture sound judgments, and judgments that I personally have always found to be reliable. Today, Ron is going to speak about IPCC's assessment process and projecting the future of climate change. So please join me in welcoming Ron.
See if I can not lose my head today. Get my slides. So my talk is going to be set up kind of like what Ram's talk was, where the first about a third of it, I'm going to go over the IPCC process. And I'm going to be hitting stuff, a little bit of stuff that both Isaac and Ram talked about before, but a lot of it's going to be from a different perspective. And then the last 2/3 of the talk will be on the projections from the IPCC of future climate change. So first of all, what is the IPCC? If you missed the earlier talks, it was established by the World Meteorological Organization and the UN Environmental Program. It was established in 1988. It's open for all the governmental members of the UN and WMO. There were full reports from the IPCC in 1990, 1995, 2001, and 2007. And from the IPCC web pages, the role of the IPCC is to assess on a comprehensive, objective, open, and transparent basis the scientific, technological, and socio-economic information relevant to understanding the scientific basis of the risk of human-induced climate change, its potential impacts, and options for adaptation and mitigation. So about every 5 or 6 years, over 1,000 scientists participate in this process, and they're from more than 100 nations. And as Michael said, their goal and their charge is to assess the public scientific literature, the published scientific literature. And many times the person running the process admonishes the scientist that it's not a review, it's an assessment. And so the goal is to come up with what you think collectively is sound scientific knowledge and where the uncertainties lie. That's what the process is about, and I'll go more into that in detail a little bit later on. And NOAA and GFDL has been a prime player in all the 4 major assessments, including the most recent one. And I'll probably mention in parts of this where GFDL models have played a role, but it's really not a GFDL talk. This is really an IPCC talk. I know this slide has lots of words on it, and I'm not going to go through them all, but this is my summary of the Working Group 1 findings, that the planet is warming, and you can see the various details there that are highlighted, that humans are the cause of the increasing greenhouse gases in the atmosphere, and by greenhouse gases I'm talking about carbon dioxide, methane, and others, that climate models using estimates of the historical forcings, greenhouse gases, aerosol, solar, and volcanoes can simulate much of the past climate variations at the global scale and at many regional scales, and I'll show a little bit of that. And as I said, the focus of the talk is going to be on the future, and that climate models project relatively large increases in warming and other climate changes in the future relative to what has occurred over the last 100 years. So there's 3 working groups. The working group that I've been involved in is called the Physical Climate Changes, and it deals with the assessing the physical climate changes, both past and the future. The second working group deals with the impacts of those physical climate changes on human and natural systems. And you'll hear other speakers during these that will be following that will talk to that subject. And then the third group has to do with mitigation of future climate changes, and you're looking at both the cost and the benefits of future climate changes. And the scientist, as I said, his goal is to assess the peer-reviewed literature, and I'm going to talk about the role of consensus and the role of uncertainty over the next few slides. Finding consensus among scientists I found to be a very messy business. Scientists seem to be much better at finding points of disagreement so they can have an argument rather than points of agreement. And it's made that observation, in fact, makes the IPCC a very interesting process. And the question that you're always trying to deal with is a given statement reflect the scientific literature, the uncertainties, and a wide range of opinions. And a lot of times it comes down to wording. And this is an example. And from the TAR, the Working Group 1 bottom line, was that there's new and stronger evidence that most of the warming over the last 50 years is attributable to human activities. That word most had a very interesting history to it. Going into the plenary, where this language had to be approved by the governments, we had settled on much instead of most. And Saudi Arabia, as one country in particular, although there were a few others, didn't particularly like this statement. And Saudi Arabia actually argued their way from much into most. And the reason was, in Arabic, the Arabic word for most was actually a smaller fraction than the Arabic word for much. Now, if you go back further into the process, the original word that was there instead of most was actually substantial. And an interesting thing happened, and I'm going to run a quiz right now, see if you guys are paying attention. What does substantial mean? Does it mean a majority, meaning more than 50% of something? Or does it mean plurality, where it could be as small as 10%, but it's the biggest part of a biggest fraction of something? So raise your hand if you think it's a majority. Raise your hand if you think it's a plurality. Okay? In the IPCC process, it was my observation that people from North America tended to believe it was a majority among the folks in the room. Now, this group actually went the other way. And people from Europe tended to think it was a plurality. And it turns out if you go to your Webster's, both definitions are there. So since we couldn't figure out what the word meant, we left it and went to much. But this is, kind of gives you a feel for what the process is like at times to argue over words and meanings of words. So when you get to the plenary, and this is a picture from a plenary, this statement, can I live with the statement, becomes very important. Is the statement wrong? Do you have a scientific basis for claiming the statement's wrong? And the scientist's role in the plenary is to make sure that the governments aren't approving language that's wrong scientifically. Now, there's different ways to express uncertainty, and 3 working groups actually have 3 very different ways, by and large, to express uncertainty. Working group 1 uses probability, likelihood of statements. Virtually certain, very likely, and so on. Working group 2 tended to use confidence statements, which is a slightly different nuance than probability. You have high confidence, medium confidence, low confidence in things. Although Ronald showed you a case on Thursday where there was a confidence statement that was associated with his radiative forcing calculation. And that's about, I think, the only place in Working Group 1 where we use confidence. Working Group 3 uses agreement in the literature, in the published literature. There's high agreement, medium agreement, low agreement, and also evidence in terms of the published literature. There's much evidence, medium evidence, and limited evidence. So you can see that uncertainty is expressed in different ways by the 3 working groups, and somebody participated in the synthesis document, which was an integration of the 3 working groups. It made it very interesting trying to reconcile confidence and agreements with probabilities. That was another exercise that made my hair grayer. So from Working Group 1, the role of uncertainty, these are the definitions that we settled on. And when you see, for the rest of my talk, these are kind of probabilities that are associated. When I say virtually certain, I'm talking about a greater than 99 probability that it's correct, or less than 1 in 100 chance of being wrong. Extremely likely is greater than 95%, so it's less than a 1 in 20 chance of being wrong. Very likely is greater than 90%, so it's less than 1 in 10 chance of being wrong. And likely is greater than 66% chance of being correct, or less than a 1 in 3 chance of being wrong. And then there's more likely and not, and then the flip side up for the unlikelies. So the role of the governments in the IPCC, when it comes to the end of the process, the scientists are writing these thick documents that are then summarized for the policymakers, and there's the summary for policymaker that's approved in the plenary. It's approved line by line, but a lot of times it's actually word by word. And as I said before, the scientists must also agree to the wording of the changes. So the wording that's in the SPM has to be consistent with the underlying report, the science of the underlying report, and he comes back to, can I live with the wording question a lot of times. And it is possible to have footnotes saying that a given country or countries did not approve of a part of the text. To my knowledge, this has never been used to date, but I've been in a few plenaries where this has been threatened. This is kind of the ultimate hammer that a session chair can use trying to get the countries to agree to come to consensus. So this is a picture that I took in Valencia, Spain this past November, of a plenary. And these big screens, you can see text, and if you're probably closer, the black text is the last version of the text that the government saw. So this is the unmodified text from the last time they actually saw the SPM. The red text, this is using track changes in words. So the red text is then what we've modified in response to government comments. And you can see that they kind of do it as a paragraph by paragraph kind of thing. And the government's down here is sitting, and they can complain about wording and whatnot, and bring up various issues. So in the plenary, typically you go very slowly through the text in the beginning. There's lots of interruptions to the flow where the government's are picky about the text and so on. And when the progress on a text stops, what happens is you end up with something called a breakout group. And a breakout group is where the scientists typically spend their lunch and suppers and nights for the rest of the meeting. They're occurring before and after the meeting. They don't occur while the plenary is being convened. And the focus is just on one particular issue. Could be just a hurricane statement or just whatever contentious statement you happen to have before you. And then the last days of the plenary usually go well into night, and I actually have not been in one yet that didn't go all night. And there's a rush to get things done. So a lot of times if you're reading the SPM document after the fact and you're wondering how in the world do people write such lousy English, it's because usually it occurred at 2 a.m. on a night after the day before we hadn't slept the night before. So it can be very, there's a big rush to get things done at the end. I'm just going to go through the process from an author's point of view because I've heard a lot of misinformation about the IPCC, like things like it's not being reviewed or the process is dominated by one person or a small group of people, which is crazy if you're going through the process. So this is my view of the state of process of producing a report. There's usually the first meeting is an organizational meeting and it occurs about 2 years before the report actually comes out. In that organizational meeting, typically you have about 10 people that are high-quality scientists from around the world per chapter. And so you get together, you find out who's going to write what inside of the chapter and who's responsible for what. And then you leave the meeting and you go out and you do a literature search and you send out emails asking for community input. And any of you in the room probably received those emails looking for input. From that input, you write a first draft. The quality of this draft typically is something akin to an average published paper because you've had 10 sets of eyes from your co-authors look at it. But it's not the quality of the final document by a long shot. And it usually goes for a limited expert review at that time. There's then a second meeting, and for the first time you get into the cross-cutting issues between chapters. For example, in the last IPCC, who was going to own the climate sensitivity discussion was a big deal. It came up in the paleo chapter, it came up in the chapter I was involved in model evaluation, it came up in the detection attribution chapter, and it came up in the projections chapter. So who was going to say what needed to be sorted out. So that's the kind of stuff that goes on when you talk about cross-cutting issues. And you plan for your next draft. And usually that second draft, again, impacts a lot of folks. And that's the publication deadline for referee papers. Any papers being referenced in the IPCC usually has to be published about right at that second draft when that's produced. So that goes out for review, and you get lots of experts and national reviews come back. Each review has to be answered individually. Both the review and the comments that how you responded to that review are made public. Typically, you get something like 1,000 comments per chapter, and then here in the projections chapter, which I'll be showing a lot of the results from today, is closer to 10,000 comments. So you're talking about 10,000 comments and about 50 pages typed. It's a remarkable number of comments. Usually a third of the author's meeting follows that. Again, you're dealing with cross-cutting issues between chapters. You figure out a plan to deal with all these comments. You write the last draft. That then goes out for both now national review, and for the first time the non-governmental organizations or NGOs get to see it. And again, all these comments and reviews are made public. And again, you get thousands of reviews per chapter. You write your final version, And the thing there you always have to pay attention to is the cross-chapter references. And you need to make sure there's a consistency between the text of the chapter summary, the technical summary, and summary for policymakers. So now I'm going to get into the projections of future climate change. This is the outline of the rest of the talk. First I'll do a review stuff that Ron and Isaac covered real quick. I'll talk about the projections. I'll spend some time talking about the various timescales of response that are in the climate system, a little bit about variability and abrupt climate change. This is a picture that I think both Ron and Isaac showed. It shows the time series over the last 10,000 years of 3 greenhouse gases. And you can see that in all 3 time series, the concentration was fairly stable to right at the end of the time series. We had this sharp uptick. The inserts are from about 1850 up to present day. And you can see that almost all the curves follow exponentials. And the greenhouse gases are all increasing, and the largest increases have occurred recently. Also, this is a picture I think that Isaac showed. This is the top panel is the globally average surface temperature observations from 1850 up to around present day. The circles are the individual years. The black line is something like a decadal smooth curve going through it. The width of the blue line is an estimate of the uncertainty in the measurements. How well do you predict where this blue-black curve really is on the curve? And you can see that the temperatures were fairly steady from 1850s up to around 1900, and then there's an increase up to about 1940, and then there's a flat period or even a slight decrease up to around 1970, and it takes off again. The middle picture is for globally average sea level. Back in the most of this period is the observations are taken by tide gauges, which are not well distributed around the planet. They typically are in the northern hemisphere where big cities are. The red curve, if you can see it right at the end, is from satellites. But again, it tells the story that the globally average sea level has been increasing, and that the rate of increase is actually getting bigger at the end of the period. The bottom panel has to do with the northern hemisphere snow-covered area, and this is now both satellites and surface obs, and you can see that there's been a decrease, and all of these are consistent with a warming world. This is another picture that Ron showed. This shows the black line is the globally average surface temperature, the observations over the last 100 years. The pink line is the what are being projected from climate models when they're forced with the best estimates of the historical forcings over the last 100 years. The blue are also climate model results where you're just forcing the models with solar and volcanoes, so-called natural forcings, not with the human forcings. And you can see a couple things. One is that the pink line does a pretty good job of simulating the observed temperature changes. You also see there's a clear separation between the pink and the blue by the end of the period, which suggests that this really is due to human activities and not just natural variability or natural forcings. And in AR4, the Working Group 1 assessment was that human activities were very likely to cause the warming. You can do that same kind of study for all the major continents, and you can see again that on each of the continents, the pink line does a good job of simulating the historical temperature changes, and that there's a clear separation between the pink and the blue right at the end. And here the assessment was that it was human activities were likely to be the cause of the warming over the last 100 years on each continent. So that is kind of assessment gives us some confidence in models. There's now been enough time passed in the IPCC where you can start evaluating the historical projections that we made back in 1990, 1995, and 2000. The black line on this graph, this is now from 1990 up to present day. This again is the observations. The blue is the estimates, the projection from the first report in 1990. The goldish or brownish color is from the second report, 1995, and the third report, the tar, is in the green. And you can see that the observations are laying right in the middle of the projections. And that's the good news. Now, this picture, usually, when I show it to a public audience, it has a big impact. But to scientists, there's a lot of issues. And it's not probably as convincing as you might think. There is no aerosols in the far projection at all. There's no volcanoes in any of them. And if you look back here in the early part, this dip here was probably caused by Pinatubo going off in 1992 or 3, forgot exactly. And the other thing is that natural variability is quite large relative to this relatively small signal. If these couple points out here in the end of the curve happen to fall down here or up here, the slope of this line could change quite a bit, and you would have a very different impression. But right now, it looks very good. And as we go out, we'll get to evaluate this more and more, because the signals probably become relatively larger, assuming there's no large volcanoes go up in the next few years. So before I get into projections, I'm going to talk about the emission scenarios that we use. The emission scenarios that we use are from the special report on emission scenarios in the year 2000, or SRES for short. And one issue is how well do those 2000 emission scenarios cover the ground that's been plowed since then by Working Group 3 type folks. And this graph shows some of that. The gray shading is kind of where the bulk of the new emission scenarios fall. The colored lines are the SRES ones from the year 2000. You can see by and large the SRES scenarios are falling into the same general territory that the newer ones are falling into. Another point to be made is that these emission scenarios depend on the future population. And all things being equal, if there's more people on the planet, they'll use more energy and therefore have more emissions, technological development, and various society choices. How efficient are we going to use our energy, and so on. How much development is there going to be in China and India in the next 20, 30 years? And where are they going to get their energy from? How is it going to be produced? How efficient is it going to be? These are all questions that determine the shapes of these curves. Now, for the SRES scenarios, there's no mitigation assumed, so there's no agreements to curb the emissions. This is just due to these factors above it. Another thing to note is that the emissions are quite different, even early in the period, and then very different by the end of the period. And I'll talk to this later, that the response doesn't look quite like that. So these are now the projections of globally average surface temperature. This panel here shows just from the model results alone. And as it turns out, two of the GFDL's two of the, I think about 20 models are in these projections. There are for three of the SRES scenarios, the so-called A2, which is a higher one, A1B, which tends to be about middle of the road, and a B1, which tends to be on the lower side of things. This yellow one down here at the bottom, I'm not going to talk about at all. That's almost a subject of a different talk, but it's one where you hold the emissions and concentrations of everything in the atmosphere at the year 2000 levels and just let the couple system slowly equilibrate with the forcing. And you can see that the temperature goes up, and in fact, this temperature will continue to go up for another 1,000 years or so, and so is sea level. So there's some very long timescales in the couple system, which I'll talk about in a little while. Another thing to notice here is that the temperature changes for up to about 2050 or so are not very different among the scenarios, even though the emissions were quite different. And you only kind of get a clear separation at the end. This shading encompasses the likely range about the ensemble mean of the coupled models. So if you come over to this, the middle part of the slide now is the working group 1 assessment of the best estimate and the likely range for each of these scenarios. And you can see that the expert judgment is to widen the bars wider than what the models do. Partly that's due to just more uncertainty. The experts are saying that the models aren't doing a good job of sampling the uncertainty space. But another reason is that it's missing, these models are typically all missing carbon feedbacks and so on. And so they're missing processes. So part of the reason these bars are wider is because of missing processes and part of this missing uncertainty. And another thing to note before I leave this is that these projections are warming, and the global average is something like a little more than a degree at the bottom of this, for the lowest of the likely range, up to something like a little more than 4 degrees over the next 100 years. And this part of the curve is can show you about how much warming has occurred in a historical period, and you can see that the projections are much larger than what occurred in the past 100 years. Now the geographical pattern that is a pattern that we've been looking at for a long time now, where the warming is greatest over the land. Before I start into this, describing this picture, this is the surface warming pattern for the end of this century minus the end of the last century. And so the warming is greatest over the land, and it's greatest in high northern latitudes, and it's the smallest over the Southern Ocean in this region, and in the North Atlantic Ocean. And along with just this pattern warming, there are also continuing the observations of the snow cover decrease. The snow cover area continues to decrease in the future. There's increases in the fall depth over most of the permafrost regions, and a decrease in sea ice extent. And in fact, in some of the projections and in some models, by as early as 2050, the Arctic becomes ice-free in the late summer. Now, for sea level changes, there was a lot of uncertainty, and there's actually a difference in the assessment of Working Group 1 and Working Group 2 here, where Working Group 1 did not make an expert judgment, Working Group 2 did, and I assume Michael, when you give your talk, you'll be talking about this. And part of that reason has to do with Working Group 2, in order to do the risk assessment, they needed to have the expert judgment. When it came to the synthesis document, we needed to reconcile the two working groups. And so what I'm going to be presenting for most of the sea level stuff is that reconciliation between the two. So the sea level, this is now the sea level rise projections from the Working Group 1 report for the end of this century minus the end of the last century. And for the lowest of scenarios, it's around 20 centimeters or so, and it gets up to around, or the highest range is around 60 centimeters or so. And this is just a model-based range. There's no expert judgment, and it excludes future changes in the dynamic glacier flow. And I'll talk some more about what that means. But it's really important to note there's really no upper bounds in these, there's no likelihood associated with this, and there's no best estimate. So why is there so much uncertainty with sea level rise? And what the report really emphasizes is our understanding of some of the important effects of sea level rise is too limited, and that the published literature on the subject at the time was really lacking. One part of it had to do with the carbon cycle feedbacks. But the most important thing has to change is in the ice sheet flow, how that's related to temperature in the future. So this is the picture, in case that you get a feeling for what we're doing. This is you're looking at part of Antarctica, you're looking at the white sheet here, and this is the Ross Sea down here. What these are ice streams. These are places where it's almost like rivers of ice flowing out to the sea, and the color shading is actually the velocities of those ice streams. And you can see that there's these almost like tributaries and rivers of ice flowing out down to the ocean. And these things are probably key for both the West Antarctic ice sheet and for Greenland, how they're going to change in the future. So the projections that I just showed you include a contribution from the Greenland and Arctic ice sheet at the rates observed for 1993 to 2003. Now the reason that period is being used is that's when the satellite observations of those changes are the best over that period. But the text goes on to note that those rates could increase or decrease in the future, and so that the upper values of the ranges are not given. And then it also went on to say that if the contribution from these ice streams, the observed rates, were to grow linearly with globally average temperature, the upper bounds of the sea level rise would increase by about 1/10 to 2/10 of a meter. Now, Ronald, Stouffer, and others have published papers with much larger values than that, but they have assumed various exponential relationships between global temperature and the ice stream movement. This is we just don't know. This is a large uncertainty here. So some other examples of regional changes. It's very likely that there will be an increase in the frequency of hot extremes, heat waves, and heavy precipitation. It's likely that there will be an increase in tropical cyclone intensity. There was less confidence in global decreases in tropical cyclone numbers. There's a polar shift in the extratropical storm tracks. There's very likely that precipitation would increase in high latitudes and likely that it would decrease in most subtropical land regions, which will be continuing the observed trends. This is a nice picture from Chris Melly looking at across the AOGCMs and that were used in AR4. The blues in this picture show places where the water availability becomes greater by the end of the century relative to the beginning of the century. The yellows and the browns are places where the water availability would go down. The colors occur in places where 2/3 of the models agree on the sign of the change. And the hatching, if you can see it, up in these regions, up in here, and a little bit around the Mediterranean area, occur in places where 9 out of 10 of the models agree on the sign. So now just getting the timescales of the response. There's all sorts of timescales here. I'm not going to talk about the timescales associated with the human and natural systems. By that I mean if today we all decided to drive Priuses instead of whatever car you drove, it would still take a while before all the Priuses or all the old cars would get off the streets. I'm not talking about those timescales. There's a lot of timescales also associated with the physical climate system. Some have to do with the greenhouse gas lifetimes in the atmosphere. I'm going to focus on the timescale associated with the ocean. And there's also timescales for the land ice sheets that are about the same order of magnitude as those found in the ocean. So one way to show this is this figure. This figure shows the relative, so you can almost think of this as the account or occurrence of certain temperature changes for 3 different scenarios. It's B1, which is the low case, A1B, which is the medium case, A2 is the high case. The oranges on here are for the 2020s, the reds are for the 2090s. You can see that the 2020 response is about the same for all the scenarios, which indicates, this is in spite of the fact that the emissions are different. This is indicating long time scales for both the greenhouse gases in the atmosphere, because the greenhouse gas concentrations aren't that different among these 3. And also the long time scales associated with the ocean. And then you can see that by the 2090s, there is now where a low case has a smaller temperature change and the high case has a larger temperature change. And one of the implications implications of this is that actions today, where you would, if you go back to the example where I said we're all going to drive Priuses, would really only have a large impact on the climate response into the future. It could be decades or longer into the future. There's some very long timescales built into the climate system. Another way to look at that is this picture. This is a picture of global mean temperature. The yellow, or the dash curve here, is a projection from a fully coupled model where you have a full ocean. So this is, you could think of this as a surrogate for the real world. And then the solid line is an estimate of what the equilibrium temperature change would be if you gave the coupled system an infinite amount of time to adjust to that. And I'm only looking at just changes due to that of the ocean, in the ocean, not for land ice or anything else at this point. So you can see that by even around the year 2000, there's almost ½ degree Celsius or more of warming built into the system by this estimate. And that the width of this estimate is a function of the climate sensitivity of both the model or the real world, the amount of oceanic heat uptake that's going on in the model of the real world, and the rate of the change in the forcing. All impacts how much warming commitment you have at any given time. So that then the anthropogenic warming and sea level rise would continue for centuries even if the greenhouse gas concentrations were stabilized at or above today's levels. One thing that shows up in the working group on report but was not brought out into the SPM, which probably should have been, which we brought up into the summary for policymakers, is that we estimated something like 0.2 to 0.6 of a meter of sea level rise per degree of globally average temperature change at equilibrium. This is a huge number. Remember I said the bottom, for the next 100 years, we're talking about a 1 to 4 degree change. So just from thermal expansion of seawater alone, if you give enough time, you would actually could raise sea level by more than a meter in almost any of the scenarios. And the word that was used in the census report, I think, is inexorable. That the sea level rises has very long timescales associated with it. So if you would, sea level would go up a meter, which is about 3 feet. What would it do to the coastline? You can see with all the yellows are places that would go underwater. So the whole southern part of Louisiana, and including New Orleans, would go back underwater. Almost all the barrier islands, including the barrier islands in New Jersey, would go underwater, and some of the Bahamas. So you can see it would be a big impact on the coastlines, and indeed would result in a very different looking world. We would lose all our river deltas and so on with a meter of sea level rise. The next issue I was going to address is the variability. How smooth a temperature increase should we expect in the future? Looking at these curves that I showed before, these curves are ensemble averages of a whole, like I said, about 20 models. You can see that they're quite smooth. So is that what we should expect or not? This is a spaghetti diagram, again from our model, GFDL, of just the temperature changes over the Atlantic Basin of SST. And there's 10 different runs in there, starting from different initial conditions where the model's being forced with exactly the same rate of forcing. So this is a measure then of just the natural variability of the system. And the question is, how do you characterize this? And you can see that they're all warming. So kind of the way the IPCC and what I just showed you to do it is to run some sort of time ensemble mean through the middle and colored black. And in this case, it just shaded the min and the max range of the 10-member ensemble. I could have did the likely range instead if I wanted to, and reproduce it exactly. Another way to characterize it is just a straight line. The warming is good. This is the rate of warming over this century. But if you go back to the wiggly lines now and just say you pick out one, there's one member of the ensemble. And if you look at just that 8-year period, you have a cooling trend over a fairly big area of the Earth, the Atlantic Basin, that this cooling trend is just about a third of the total warming trend that you expected. And this is just due to natural variability. There's no radiative forcing changes, no volcanoes, no changes in anything at all, just natural interactions between the atmosphere and the ocean, the land surface. So this is how that one ensemble member fits into that shading region. You can see it went from being the kind of the warmest of the group to the coldest of the group during that period. You can see it did it again at the other end of it. This is just natural interactions. Which brings us to this past month. I don't know, this has been making a lot of news. In January of 2008 was a very cold month globally. And so I've heard all sorts of descriptions of just how cold it was. I've heard people say that it wiped out all of the global warming of the last 100 years and so on. So this is a time series from, I went out to the GISS website and just downloaded the picture. This is the globally averaged monthly trend from the GISS website from 1980 up to last month. And you can see here's the very cold January. And indeed, it doesn't wipe out the whole 100 years. It wipes out about to 1994. The other thing you can see is that a drop of about this magnitude isn't particularly unusual. There's one right here. There's one back in here, and so on. And so, what's the cause of this particular drop? At least part of the answer is that there's a La Nina going on in the tropical Pacific Ocean. The tropical Pacific is colder than normal, and it's a large chunk of the planet right there. And it's also, if you look at the maps, you can see that it's just probably natural variability over the northern hemisphere continents. This strip across southern Eurasia was very cold. It was one of their coldest on records. But just north of that was one of their warmest on record. So it looks like it's just natural variability. So then just to finish the talk a little bit about abrupt climate change. Anthropogenic warming could lead to some impacts that are abrupt or irreversible, and that they depend on the rate and the magnitude of the climate change. And the one that people talk about a lot is the loss of ice sheets on polar land, which would imply meters of sea level rise if they would melt. And they would obviously then cause major changes to coastlines and inundation of low-lying areas, and the greatest effects would be in river deltas and low-lying islands. In Working Group 1 report, we projected those to occur over millennial timescales, but more rapid sea level rise on the centennial timescale couldn't be excluded. Another candidate for abrupt climate change is the overturning circulation in the Atlantic Ocean. Now, this is a cartoon over here on the left. Most oceanographers don't buy anything to the right of where my arrow is right now. So if you just focus on the Atlantic, you have warm, salty water flowing northward at the surface. It gets up into high latitudes of the North Atlantic where it's cooled by the atmosphere and it sinks to depth. And it flows out of the basin as called salty current, where it flows into the Southern Ocean. It's mixed. This overturning circulation is projected to slow down during the 21st century. It's very likely, according to the assessment. This overturning circulation, as it's flowing north, I said it was a warm current. It actually brings quite a bit of heat to the northern hemisphere. In particular, Europe owes some of its warmth to the fact that this current exists. And so that even though the current is slowing down, the Atlantic and the European areas are projected to have temperature increases, as you saw from the map I showed earlier. That the assessment was also that this overturning circulation is very likely to undergo a large abrupt transition during the 21st century. I mean, we didn't expect this to have a surprise. but that longer-term MOC changes cannot be assessed with confidence. So just in summary, the IPCC is a successful mechanism of communicating climate change science to both policymakers and to the public. The IPCC can influence policy through governmental actions. I can't stress enough, one of the things that struck me the first time I went to a plenary was the importance of the government approval of the SPMs. And when you get there, by the time you come out of the plenary, you had the governments more or less agreeing to the science, so that when the next round started, say when Kyoto started, or in this case, we just had a meeting in Bali, and there's going to be other meetings that follow on, where governments are trying to figure out what to do from a policy point of view. Now that they understand the science, that you can kind of divorce the policy arguments from the science arguments. But that's not to say that people still won't make science arguments while they're discussing the policy changes. They do. But the bulk of the science is settled before you get into those negotiations. I showed you the projections of climate change for this century are going to be larger than what occurred in the last century. That the response time scales of the climate system and natural variability complicate the discussion and hinder understanding. And that we know a lot about future climate changes, but some surprises are still expected. That's it. Thank you.
Just curiosity, how did scientists get selected?
That's a good question. I'm not sure I understand the full way they're selected. The process is twofold. The countries nominate scientists for the IPCC panel, and also the chair of the working groups have their own selections. And then I think the chair picks, say, the 10 people for each chapter and submit them to the IPCC Bureau when they're approved. I think that's, you know.
But the convening lead authors have to be approved by countries. Yes.
I thought they all did.
That has to be done in the plenary.
Yeah, that's done in the plenary, but I think they all,
Authors,
I think they all do, because it has to be the
lead authors could be, I would have never been approved whether you were any process in this government. Lead authors have to be approved by the Bureau of
Yeah, maybe that's how it goes. Yeah, you're right. Okay. There's a thing, a panel called the Bureau, which kind of manages the IPCC nuts and bolts that goes on. So there's kind of two levels. There's a plenary where the countries approve the CLAs, and then the Bureau would approve the LAs. And they're looking for how much of a representative across the countries there are, for each of the lead authors, a wide range, both in terms of continents and countries and so on.
Have you given any measure to how far off the line reality would have to go before it could be concluded that the projection needed to be readjusted in either direction? Well,
that's a good question. The question is, how far wrong does it have to go before you know it's wrong?
Yeah.
No, that's a good science topic. I don't know if there's been any literature written on that.
Well, wait to restate that question.
Yeah.
In the past 5 years, there's a lot of revision of my report. How much of that was the result of what nature told us in the period that was being available? 5 years roughly, and a year or two before. And then you have nature telling us its story.
Yeah, it's hard to... Right, but it's hard to... When you pose the question that way, it's actually really hard to answer it, because at the same time, you're getting you're getting more data to evaluate and develop models against. So there's kind of two sections of that. When you're developing a model, you're comparing it usually to some sort of time average observations. And then, when you do the historical forcings part of it, which you do after the model's developed, you can then make an evaluation of how well the model's doing against that signal that you're seeing. And the more years of record you have, the bigger the signal's been. So there's kind of two different ways to look at that.
I have a question about the narrowing of uncertainty over time. I'm struck that the warming due to the sea level rise due to the warming of the ocean seems to have a factor of 3 uncertainty, 2/10 to 6/10 of the meter for what, 3 degrees?
Yeah.
Term average?
That
Why is that so? If this is expansion of water, what is it that makes some things?
We don't know.
That's so uncertain.
We don't know what the temperature changes with depth are going to be. It's as simple as that. A lot of these simpler, to get at that, we have to run models to equilibrium. There's not been a whole lot of models, complicated models, run to equilibrium. And what's going into that factor is really how much warming is there going to be at depth in the ocean. Turns out that models, the simpler models all project that the warming actually at the end is going to be relatively uniform. So if you have something like a globally average 3-degree temperature change at the surface, the whole ocean basically warms up about 3 degrees. Now, if it's 2 degrees, it'll have a big impact on that range because all of that, a large fraction of that range is coming from the temperature changes at the bottom of most of the ocean.
But is that a variable that will shrink over time?
I doubt it. It'll take a long time for that error bar to shrink. That's one that will probably stay wide or even get wider as we learn more. I think this is the first time people tried to estimate that particular number.
But other error bars are shrinking.
Some are, some aren't. I mean, the error bar due to clouds isn't much different than it ever was. That's an example. Yes?
You mentioned that the government's role in the review of the assessment reports help get them on board. But the flip side of that is people who may perceive there to be government meddling in the versions of the report that are published, compromise the uncompliance and make sure that the findings. So I was wondering if you could comment on to what degree the government has actually impacted what the scientists presented in their drafts.
By and large, I found the process actually fairly innocent and not nearly as draconian as what it's made out to be by the people on the outside of the process, where by and large, the process is improving communication of the science to policymakers. And it's not trying to make it policy prescriptive or fit into somebody's preconceived notion. There's just too many people involved to do that, in my opinion. I know that the early release of the reports, which I guess is now going to be standard operating procedure, every time a draft of the IPCC report is developed, you'll see it in the New York Times the next day, I guess. I think hurts the process because if anybody that writes any scientific document knows that drafts are just that, they're drafts. You're looking for ways to say things. And there's going to be times where you can say things better and say things worse. And the process is trying to weed out those bad ways of saying things. And so it can lead to the appearance of tainting the report one way or the other. But actually, from the inside looking out, I've found it fairly innocent, where, yes, there are scientists that have preconceived notions, but that's where, some other scientists don't, and that's where the arguments occur among the scientists. The government's role, so by and large, there are exceptions, but by and large, in the plenaries that I've been in is helping the communication occur, not hurting it. Yes.
Has anybody talked to the government of Dubai about all those little islands they made?
I have no idea. Any other questions? Yes.
Yeah, we have these 4 rounds of assessment. So through this process, what do you think the biggest improvements they have made? And it's about to make it more information.
The whole process. The thing, if you look back into what was going on before the IPCC came on the scene, I wasn't too involved in the process, but I was a spectator watching Suki and others in the process, where I can remember him saying many times that he spent a lot of time writing reports that nobody read. The scientists understood that they had an important thing to communicate, and they were looking for vehicles and ways to communicate. And you could never really tell when you were involved in a particular document whether that document was actually going to be read by somebody or somebody's that mattered. And so as a scientist, you typically have 1 or 2 reactions to that. Either you dropped out of the process altogether and said, it's a waste of my time, I'm not going to do it. Or you fully immersed yourself in that process and wasted a lot of your time. And so it's kind of one or the other. And whereas when the IPCC came along, there's such a transparent and clear undertaking that did entrain a large fraction of the climate community. And it did an effective job of communicating the science that it really changed the landscape quite a bit. And it was, clearly all processes are flawed, but this is one that's not as flawed as a lot of what it replaced. And so I think it's been very effective, as I said.
So in the future, what do you think that's the weakest point that IPCC still have, and how can they improve that?
The weakest point is probably its success. As is in most cases, the AR5 is what in the next report is being discussed right now. In the IPCC, there's all sorts of proposals about for what it should look like. On one hand, they're talking about keeping it more or less the way it's been, where you have 3 reports, structured kind of like what I just described. On the other hand, they're talking about going to a whole bunch of small reports, being very topical. So you would have impacts and adaptation and physical climate things all inside of one report. And I've heard things like not to have a working group 1 report because it's a settled science now. That seems crazy to me, but yes, I've heard it. So, there's supposed to be a meeting next month to discuss by the IPCC to discuss just how will AR5 look in the future. Now, in terms of, I forgot it. I had a thought and lost it. But the future, in terms of, if they keep it the way, one of the big advances in AR4 was the organization of the Working Group 1 community, where all these models that I showed ran on a common framework. It was a grand model and comparison project. And I think that data was all collected at one institution, and all of you go get it if you wanted to, and a lot of you have, and analyze model data and conduct climate change science if you wanted. It's publicly available. That organization, I think, was a big step forward for the Working Group 1 community. One of the proposals for AR5 is now to have Working Group 3 and Working Group 2 do similar organization and actually then have interactions between Working Groups 1 and 3 and maybe even 2 on relatively during the process of writing the reports. To date, these reports have been almost independent. There's been very little crosstalk between the reports. And I think something that needs to change in the future is there needs to be a lot more crosstalk between the three reports. And hopefully that'll change in the AR5. Okay.
Well, actually, I'll ask you a second question that leads up to one of the next few. I'm going to ask you, well, two questions. One is the IPCC from the science department, is it a top-down, a bottom-up, none of the above type of organization? It's not random. I mean, that's
No, it depends on actually what you're thinking, how you're thinking about it. As an organization,
well, how do you organize the working group one? How do you get that process started?
that's all top down.
That's top-down.
It's a bottom up in the sense of the writing of the reports and you know what's in the report. That's very much a bottom up. But the structure of the thing is, you know, is sure can, right? It's very top down.
The other thing I was asking, which you showed those wiggly lines for the emissions, kind of going, most of them going up and some going up and down and things. At least in the physical climate part, most of the lines go up.
Yep.
How are you going to incorporate what looks like even the biggest uncertainty, which is what are people and technology and population left technology and societal decisions going to do over the next 100 years? Is that going to be approached differently? That's maybe a Jay Evans question.
Yeah, that's a much better question for Jay than us. But this interaction I was alluding to between working groups 1 and 3 is actually trying to address some of that, where for AR5, instead of these unmitigated scenarios being the focus, it's actually stabilization scenarios where the concentrations go up and flatten out at some point in time. And there's going to be kind of a high, a medium, a low, or maybe two mediums, a high, two mediums, and a low set of scenarios to be run by the models. And one of the things when the Working Group 3 community developed these so-called stabilization scenarios, they have very simple climate models with simple carbon cycle models. And for the first time, if we run those same scenarios, they can then evaluate their simple models against our much more complex models and look at see how much uncertainty they really should be assessing, because some of their stabilization scenarios may not be stabilization scenarios when you run a more complicated model. So I think that's where the big advance could be in terms of communication for AR5. Yes.
This is also not a strictly Working Group 1 question, but you noted that now that time has elapsed over the several assessments, you can evaluate in natural science how accurate or not accurate it's been. I was wondering if there's been serious work on assessing the assessment in terms of sort of the social science, empirical impact on government, intergovernmental, and whether that's sort of ongoing and going to be brought into the future.
That's a great question. I've asked that same question myself, and I haven't got a good answer yet. I think my intuition is no, but I'm not sure that that's correct.
Any other questions?